In this video, I am going to introduce the concept of the VC dimension. VC dimension is a concept invented by Vladimir Vapnik and Alexei Javodenkis. It can be thought of as a measure of the size of a set of functions or a set of sets. Crucially, this measure is intimately connected to the notion of pack-learnability we discussed in a previous video through the so-called fundamental theorem of statistical learning. But before getting to all of that, let's first try to really understand the VC dimension in this video. To do so, let's start with the example of threshold classifiers that give label 0 to everything on the left and label 1 to the features on the right. The space H of such classifiers is the set of functions with a threshold theta, such that all points on the left of theta are given label 0 and all points on the right are given label 1. Evidently, the space H of such threshold classifiers is infinitely large. I can put theta wherever I want. But it's also highly structured. In fact, it's tempting to say that H is only of dimension 1. Actually, its VC dimension is indeed 1. To see this, notice that if I take 2 points on the line, then not all classification of these 2 points are possible. I can classify them as 0, 0 by taking the threshold on the right, or as 1, 1 by taking the threshold on the left, or even as 0, 1 by taking the threshold in the middle. However, I cannot classify them as 1, 0 because no matter where I put the threshold, I will not obtain such a classification. We say that any set of 2 points of the line is not shattered by threshold classifiers with zeros on the left and ones on the right. More formally and more generally, consider a set X of features, 0, 1 labels, and a set H of prediction functions. We say that a subset P of features is shattered by H if any function from P to 0, 1 is the restriction to P of some function of H. In other words, no matter what samples from P I observe, I will always be able to find a hypothesis of H that fits the sample. Now, intuitively, the more a space H of functions shatters things, the larger the space is. While the VC dimension is actually precisely defined as the cardinal of the larger subset P of features that H shatters. Getting back to our threshold classifier example, we have shown that no 2-point set is shattered. Thus, the VC dimension of H is necessarily strictly less than 2. However, evidently, any 1 point is shattered. Indeed, by putting the threshold on the left, I can set its label to 1, and by putting the threshold on the right, I can get it to 0. This means that I can construct all functions from the singleton that contains only this point to the set of 0, 1 labels. Any labeling of this point can be obtained from an element of H. Thus, the VC dimension of threshold classifiers is at least 1. So it's at least 1 and it's less than 2, and the VC dimension is defined as the cardinal of some set. So necessarily the VC dimension is integer. This means that it's going to be 1. Now, if we allow threshold classifiers to invert the order of labelings, that is, giving label 1 to all features on the left and label 0 to all features on the right, in addition to the threshold classifiers that give label 0 on the left and 1 to the right, we obtain a larger set of threshold classifiers we'll call K. Then K shatters all 2-point sets. Indeed, we can now construct 1, 0, the one that we couldn't construct before, by putting the threshold in the middle, and by giving label 1 to features on the left and 0 to those on the right. This shows that the VC dimension of space K is at least 2. However, it actually cannot be 3 or more. Indeed, we cannot achieve a classification that's 0, 1, 0. No matter where I put the threshold, I will always have at least 2 of the 3 features on the same side with respect to the threshold, and these 2 features will disagree with one another, which is inconsistent with the threshold classifiers. Thus, the VC dimension of the space K is actually strictly less than 3, so it's going to be equal to 2. More generally, it can be shown that the space of linear classifiers of R to power D has VC dimension D plus 1, and I will prove this in a future video, link in the description. Let's consider another easy example to really grasp the concept of VC dimension. Consider classifiers that correspond to drawing a rectangle aligned with the axis and giving label 1 to the points inside the rectangle and zeros to others. Can you guess the VC dimension of this set of classifiers? It turns out that the VC dimension of these classifiers is 4. To prove this, let's first determine a set of 4 points that is shattered by axis-aligned rectangles. Take the 4 cardinal directions. I can verify that any of the 2 to the power of 4, which is equal to 16 labelings of zeros and ones of these 4 points, can be fit with an axis-aligned rectangle classifier. It's a bit cumbersome to do, it takes a bit of time, but it's really not difficult. Now, let's show that any set of 5 points is not classifiable by axis-aligned rectangles. To prove this, we'll give label 1 to the one that is most in the north, 1 to the one that is most in the south, 1 to the one that is most in the east, and 1 to the one that is most to the west. Then there will be 1 point left, which is the point in the middle. Let's give it label 0. Then no matter how hard you try, you will not be able to draw an axis-aligned rectangle that contains all points but the one in the middle. Indeed, if you draw a rectangle that contains all points on the outside, it will necessarily contain the one in the middle. This shows that for any sample set of size at least 5, there exists a labeling of these points that our hypothesis class cannot fit. Thus, the VC dimension of axis-aligned rectangles is less than 5, and in fact it is 4. Finally, probably some of the most useful VC dimensions are the ones of finite hypothesis classes. Since any set C requires at least 2 to the power cardinal of C classifiers to be shattered, we know that if H shatters C, then H must have at least 2 to the power cardinal of C elements. In other words, by taking the base 2 logarithm of both sides, we obtain the inequality cardinal of C smaller than the logarithm in base 2 of the cardinal of H. And this proves that the VC dimension of H, which is the cardinal of the largest such set C, is at most log base 2 of H. However, these two quantities may not be equal, and in fact we have just seen a lot of examples in which hypothesis classes had infinite cardinalities but finite VC dimensions. I hope that this video has helped you better understand the concept of the VC dimension. Once again, the VC dimension of the hypothesis class H is the size of the largest subset C of features that H shatters. In future videos, I'll compute the VC dimension of linear classifiers. And in still another video, I'll state the fundamental theorem of statistical learning, which relates the two fundamental concepts of pack learning and of the VC dimension.